Hi, and welcome to a special episode of Operating Systems. Special for two reasons. One is I'm having to record this remotely, and the other is we get to talk about a different topic today, Cuda, or the Cuda programming language, and GPU programming in general. I know that you've had a chance to write a lot of multi-threaded programs this semester, and you can see that's, or hopefully you've seen that's a great model for taking advantage of multiple CPU cores and for writing a program that can respond to a lot of different things at once. Today we're going to see a way to write a program that can take advantage of a lot more computing cores, but under a special programming model. We've got some demo programs we'll take a look at. We'll play around with those a little bit, and we'll talk about how GPU programming in general works. The model we're going to be using is Cuda. You'll find it is a lot like the C programming language. It's designed to be mostly C with a few extensions that let you write code specifically for the GPU. This is a model that was developed by NVIDIA, and it would be described as general purpose GPU programming. I guess the observation quite a few years ago was that GPU or graphics processors, your graphics card in your computer, had a whole lot of computing power on it. And if we could do more than just render polygons really fast with that, we could solve a lot of different programming problems. And that's where the idea of GP or general purpose GPU programming came from. One nice thing about Cuda is even though graphics cards are all different and they have different capabilities and they have different sort of number of parallel tasks they can handle, Cuda gives us a way of trying to factor out those little differences so that we can write one piece of code and it can target a bunch of different models of graphics processors. When we're writing a program with Cuda, we really write a mixture of code that's going to run on the general purpose CPU, just like code we've always written in operating systems class and in your other classes, but we can mix it in with code that's going to run on the graphics processor. We'll think of it as kind of a graphics coprocessor. Cuda lets us mix those together in the same source file, so it's easy-ish to manage a program that includes some GPU and some CPU components. We'll still take advantage of the general purpose CPU, but we will think of we'll think of it as a model where as we're solving a large computationally expensive problem, we can take some of the more expensive subtasks, ones that admit or invite parallelism, and we can farm those off to the GPU so the CPU doesn't have to do them, and so that the GPU can usually bring more parallelism to bear in solving those problems. I'd like to talk a little bit about the difference in general between the CPU, the model of a processor that you've been programming for up to this point, probably, and the GPU. So a CPU, I drew a picture over there that shows how you can think of it. It has, I guess years ago, a CPU might have had one processing element in it. It could run one sequence of instructions at a time. But as we've talked about when we started talking about multi-threading, modern CPUs usually have multiple cores. So they can be running multiple little bits of code out of usually different regions of memory, all at the same time. So the picture I've shown, they have a number of processing elements, but it's usually a smallish number. So they might have 4 or 8 processing cores in the CPU, each of them capable of running their own program. So each of those cores has its own control, meaning it keeps up with where it is in your code. Each of them could be running a different section of code. Each of them is keeping up with its own copy of things like CPU registers. So we usually program this model so that each of those cores can run independently, keeping up with the instructions that it's running. We usually build a general purpose CPU so that each of those cores can run really, really fast. And that means usually putting a lot of cache between this CPU or between its processing cores and memory so that we don't have to wait on memory as much. A GPU has some of the same ideas, but it exploits a different trade-off in sort of how you're going to use the real estate of that processor. For one, on a GPU, we're going to build a lot more processing elements. So if a CPU might have 4 cores, a GPU might have hundreds of processing elements that let it do math, that let it access elements of memory, that let it save stuff in memory. And these can all be computing things all at the same time. We can't, but if we're going to say, well, let's build as many processing elements as we can, there has to be some kind of trade-off, and usually that's in the form of reduced cache. So a GPU may not spend as much processor real estate caching memory, which means its processing elements individually are probably going to be a little slower than they would be on a general purpose CPU, even though we have a lot more of them. And usually they're all going to share one control, meaning they're not all free to run their own sequence of instructions. They can't be running in separate parts of the same program. It's as if they're all doing the same instruction, maybe on different regions, or typically on different regions of memory, all at the same time. So you can imagine, kind of like I've drawn, the control is over at the left, at least in my picture, and you can think of it as sort of telling all of the processing elements what to do, and then they all do it at the same time. But they're all operating on different regions of memory. So if you had to, say, add a value to a bunch of array elements, you could tell each of the processing elements to work on its own part of the array, and then they could get the job done faster by each adding to their assigned part of the array. This is a typical of a SIMD, single instruction multiple data model of computing, where we've got one control, but we can use it to drive a bunch of different processing elements. If you have a computing application where you have to do the same thing to a lot of different parts of memory, this model can get it done a lot faster by, well, a lot faster than having a single processing element, by being able to execute a lot of those instructions in parallel. So I hope I did a good job explaining that. The way we're going to use these, kind of like I've hinted, is the CPU, the general purpose CPU, can usually support a modest number of threads, each running their own section of code, maybe each running in a separate process. That's what I tried to draw over there on the left, those little squiggly arrows. That's a typical notation for a thread, and I colored them each differently to suggest that they're each running their own bit of code. A GPU, because it's got a lot more processing elements, it can support a lot more threads running concurrently, but they're all going to be doing the same thing. They're all going to be running the same bit of code and even running the same instructions in that code, but typically operating on different data at the same time. In the Cuda model, we have to think about organizing our code into what they call blocks of threads. The GPU can run a bunch of threads at once, and a block is the Cuda term for a collection of threads, maybe tens or hundreds of threads, that are all running at the same time, that all have access to some shared memory, so there's a region of memory that they can all read and write from. They have the ability to since they share that memory, they can cooperate on things, they can communicate through that memory, and there are even some synchronization primitives so that they can coordinate their activity. But because they share memory and because there are mechanisms for synchronization, we have a limit on the number of threads that we can put in a single block. So normally a task on a GPU is broken into a lot of threads per block, and then if that's not enough, we'll break those into multiple blocks. That's what I tried to draw in this picture over to the right. So however many threads you need to solve your computing task, we'll break that into usually a fixed number of threads per block, and then the GPU will take care of running those blocks one after another, or at least running through all of those blocks, giving them each a chance to execute. Like I've tried to show in the picture, if I've got a lot of blocks to run, the GPU may have to process them serially. So it'll run the threads in one block, and then it'll start working on the threads in the next block. Since it's running each of the blocks serially, that means between blocks you can't share memory. You can't communicate between those threads because they're not all running at the same time. So this is sort of our mechanism for handling lots and lots of threads. Every block might have tens or hundreds of threads in it, and if that's not enough for what you need, you can break your compute task up into multiple blocks, and then the GPU will take care of running through those blocks as quickly as it can. This picture I've shown here is kind of the point of breaking up the computation at two different stages. If you've got a lower performance GPU, you might only be able to run one of those blocks at a time. But if you have a more powerful GPU, or if you have a lot of GPU devices, you could even parallelize those. So a more powerful graphics processor could get through that set of blocks more quickly by running several of them in parallel. The nice thing is, as the programmer, you don't have to worry so much about how these blocks are getting scheduled on the GPU. You just describe your task as a bunch of threads within a block, and then a bunch of blocks, and the Cuda infrastructure takes care of scheduling that on the GPU for you. So a more powerful GPU would get through all of those blocks faster. I've been avoiding saying this term because it wasn't on my slide yet, but a collection of blocks is called a grid. So every grid has a bunch of blocks. So a compute task is a grid where every grid is made up of multiple blocks, and every block has a bunch of threads in it. Each of those threads has a unique index, and that's kind of, as you'll see in our example program, that's kind of how we give each thread a different job to do. When a thread wakes up, there's a mechanism that lets it figure out what its index is, and then if you've got a bunch of, if you've got a giant array of data, it can use that index to decide which element or which elements of that array it's responsible for. Now, I've simplified things a little bit, and I'll briefly mention how I've simplified them, but then I'll go back to sort of talking in this more simple model. I've described blocks as if they're kind of a list of threads, and I've drawn pictures that sort of show them linearly organized, and I've done the same thing with blocks. I've shown a grid, like in my top picture there. I've shown a grid as a list of blocks. You can build your, you can organize your threads like that, but you don't have to in a GPU, since a lot of times you'll have tasks that pertain to working with an image. It might be natural to organize your grid two-dimensionally and to organize your threads within a grid two-dimensionally, so that each thread might have responsibility for some of the pixels on an image that you're displaying. That's a nice feature. It's built into the Cuda programming model. It's just not a feature that we're going to use, at least the multi-dimensional part of that. So even though we could do it, we're going to think of our threads, or we're only going to use the first dimension of this. I mention it because when we start looking at the API for doing this, you'll see that based on how it's named, it'll be kind of obvious that this thing could be multi-dimensional if you want. I'll mention one more thing. So you can see in the middle of my slide, I'm talking about how every thread within a block has an index, and every block within a grid has an index. And that index could be multi-dimensional, but it doesn't have to be. One nice thing about Cuda is it provides that index for you. You may remember when we've done parallel computation with something like p-threads, we had to worry about passing parameters to our threads. P-threads provides a mechanism for that, but if you wanted to make a bunch of threads and give them each a different job, you had to use that, typically, you would use that parameter passing mechanism to tell each thread, what its index is, or to carve up a computation task, and then tell each thread what part of that task it had to do. A nice thing about Cuda is it does that for us. As soon as a thread wakes up, it can look at some of the Cuda data structures and tell what its index is without us having to write code to communicate that index. So we sort of get that for free with Cuda, which is nice. Like I said at the start of the description of Cuda, we can, if we're going to do a large computation task and we're going to take advantage of the GPU, you can think of that task as being split between some operations that run on the general purpose CPU and some that run on the GPU. And that's what I've shown at the bottom of this slide. The CPU gets to gets to start the computation task. So if you're writing something in Cuda, you'll still have a main, and when your program starts up, there will be a single thread running in main. You can compute with that thread, but then when you get to a big computation task, you can write code that pushes that out to the GPU. That's what I've tried to show. So over on the left, you can see there's a thread that computes for a little while, and then it shoves a grid of blocks over to the GPU. It shoves a computation task over to the GPU, lets it compute there, hopefully a lot faster, and then gets results back from the GPU. And then it might compute a little bit longer on the CPU and then farm off another task to the GPU. I hope I haven't made, so this is convenient, it's a nice programming model to work with, but I hope I haven't made this sound like it's automatic. The Cuda model gives you a mechanism for doing this, but it's still up to the programmer to decide what parts of their computation are going to run on the CPU or the GPU, and to write the code that actually does that computation on whichever resource it's going to have to compute on. I've been avoiding using these terms at the bottom of the slide because we hadn't talked about them yet, but usually we'll talk about code that runs on the general purpose CPU as running on the host. And instead of having to say GPU over and over again, we'll usually use device to describe that. I guess a nice reason for calling that something like device is, well, you might have multiple graphics coprocessors, and they ought to all be able to work together. So if you farm off a computation to your device, maybe it's going to run on just one GPU, or maybe it's going to be able to be parallelized across a lot of them. So this is the model we're going to work with. For the homework assignment we're going to do with Cuda programming, and for the example we're going to look at later, we only, well, it's simpler than this picture shows. We're only going to farm off one compute task and then wait for that to finish. But for a bigger task, this could happen multiple times. So you might compute a little bit on the CPU and then do some work on the GPU and then back to the CPU, again, several times around. So let's talk about what kind of code we need to write. Let's talk about what our code's going to look like if we're going to write some stuff that's going to mix GPU and CPU programming. Cuda lets, like I said earlier, it lets us mix all of this code in a single source file. But when it compiles our code, it needs to know, well, do I compile that for the CPU or the GPU? Because they may have different instruction sets. So the machine code that runs on one of them might not be able to run on the other. So Cuda gives us a mechanism for marking stuff that should run on the host. And that's it right there at the start of this call. So if you want to write a function and you want to say this is going to run on the host, you put, I think it's double underscore host and then double underscore, and then write the function the way you normally would. And then the Cuda compiler will build that, compiling it to machine code that runs on the host, on the general purpose CPU. If you want a function that can run on the GPU, you put the word device in front with, again, I think double underscores before and after it. This function can take parameters. We'll see an example of this in a moment. But marking it with device tells Cuda to compile that for the GPU. One thing to keep in mind is, well, if the host and the GPU, if the host and the device are separate, we can't depend on them sharing memory. So you can see in this example function, that function at the top that runs on the host, I put a note there that says, well, if you pass it a pointer, that better be a pointer to memory that's in main memory, that's in the host's memory. But the GPU also has its own memory. If you call a function that's going to run, or I guess, if you call a function that's going to run on the GPU, you can give it a pointer, but it's got to be a pointer to something in the GPU's memory. I've got a picture for this. I'm going to run ahead a little bit so I can show you this picture, and then we'll go back to look at that code. So this is kind of what I had in mind when I was talking about that. The host has a CPU, and this is what you've written most of your code for so far in computer science. And it's got a big collection of main memory. We spent a couple of chapters talking about this model. On the GPU, or on the device, we may have one or more GPUs, and they have their own memory. So if we want part of our, if we want the device part of our program to be able to access something in its memory, we're going to need to be able to copy it into this GPU memory. And we'll see that there are some functions that let us copy things back and forth. All right, so backing up to where we already talked about this. So here's how you mark code for where it should be able to run. It tells the Cuda compiler what instructions to use when it compiles it. We talked about code that's running on the host. We talked about code that's running on the device, but we also need to be able to make a transition between those. And that's what I'm trying to show here. So you can write a function that runs on the device but is callable by the host. And this is really how you start a computation that runs on the GPU, that runs on the device. So your program will start at main, it can call other functions inside that program, but when it wants to run something that runs on the GPU, or when it wants to call some code that runs on the GPU, it's going to call a function like this my function, marked with this global keyword in front, and again, I think two underscores in front and two underscores in back. When you call code like this, it's called a kernel. I know we've used that term a lot this semester, usually talking about the kernel of the operating system. This is the same word, but it means something different here. Think of it as a chunk of computation that's going to run on the device. It's special because a function that's going to do the job of a kernel has to be marked global like this. So that means it's called from the host, but it runs on the device. And when you call it, you have to pass in some extra stuff. That's what I'm trying to show down there at the bottom. That funny looking piece of code is a function call. And parts of it look like what you'd expect. Like here's the name of the function you want to call in front. Here are its parameters out here in back. This stuff in the middle, well, those tell the geometry of the grid and the blocks in the grid for running that kernel. So when you farm off code to the device, it's not going to run on just one thread. It's going to start it up running on hundreds or thousands of threads all at once, or as fast as the device can schedule them to run. So when you start this up, you don't just say what function you want to call, you don't just pass it parameters, but you also inside these triple angle brackets. So less than, you give how big the grid is, so how many blocks are in the grid, and then how big each block is, how many threads are in each block. So this is sort of how you pick the geometry of the parallel computation task that you're going to farm off to the GPU. So here's pretty much the same code we looked at before, just with some notes on it. And I think we may have already said all of this. So global marks a function as running on the device. When you call it down here at the bottom, you get to pick how many threads call it. When you pass it parameters, well, if they're parameters that are primitive types, like this integer a, Cuda takes care of passing that parameter to every one of your threads at once. So down here, if you say, make me a block of 50, make me a grid of 50 blocks, each with 50 threads, it'll take care of starting up and scheduling all those threads, and it'll take care of giving them all a copy of whatever your parameter A is here. It'll even give them a copy of this parameter B list. But since that's a pointer, you have to be careful with that, because if you're passing a pointer to code that's going to run on the device, like I said before, it better be memory that's allocated within the device. So when you call a function like this and you give it a pointer maybe to the data it's supposed to work on, you have to worry about making sure that pointer points to data that thread can access when it starts executing. And we'll see an example of this in a moment. So like I said, we're down here at this last bubble. The nice thing is every thread wakes up and it automatically gets a copy of whatever parameters you pass in. So you don't have to, comparing this to p-threads, you don't have to do as much work making sure all of your threads get these parameters. That's taken care of for you. But you do have to worry about, what resides in what memory. And this is the figure we jumped ahead to a moment ago. The host has its own memory, the device has its own memory. And if you're going to write code in Cuda, you have to worry about what memory various data structures reside in. Normally, and in the code that we're going to write, the program's going to start running on the host. It's going to load in, if we're going to work on data that's loaded from the file system, it's going to load that into host memory. But before we run a kernel, before we run something that's going to run on the device, we're going to have to execute some instructions that copy that data over to device memory. And that's what I'm trying to show in this picture. There are functions that let us do this. Normally this will mean we'll have to allocate some space on the device. We're going to have to remember a pointer to that space, but it's the address of memory within the device, not within host memory. So that means we can store that pointer on the host. We just better not dereference it because it's not a meaningful pointer for the host. So we can ask for memory on the device. We can call functions that copy things from the host to the device. And then when we run a kernel, if we've done that, if we've allocated memory on the device and copied some data over, that data should be there on the device when our threads start up. The functions we need to do this, like I said, we'll need to be able to allocate memory that's in device memory rather than host memory. So that sounds a lot like a job for malloc, and there's a version of malloc for Cuda. So the malloc that you already know works fine if you just want host memory. But if you want to ask for memory that's allocated on the device, this is what you're going to need to call. So Cuda malloc, it's kind of like malloc, but the way it uses its parameters is a little bit different. Just like malloc, you tell it how many bytes of memory you want. So that's the second parameter out here. If you've got a number of items like count here, if that's how many items you want, and each of them is an integer in size, this will allocate enough space for that many integers on the device. You'll remember malloc gives you back your pointer by returning it. Cuda malloc expects a pass by address parameter for that. So this first parameter is kind of like the return value for your pointer. To use Cuda malloc, like I've shown, you have to make a pointer beforehand, and then when you call Cuda malloc, you give it the address of your pointer, and it fills in that pointer with the address of whatever memory it can find for you. Why didn't it just return that pointer? Well, I don't know if it's all the Cuda functions, but I think it's all the ones we're going to see use that return value as a success failure indicator. So they already used the return value to tell you something else, to tell you whether or not this worked. So the pointer they give back to you has to be given back through a pass by address parameter. So this top function is how you ask for memory on the device. Backing up a slide, if you have some data in host memory and you want to copy it to the device, normally you'll first allocate some space on the device using a function like this. Then you'll copy your data over, and this function Cuda MemCopy does that for you. It'll copy either way. It'll copy between host memory and device memory, or the other way around. This second parameter decides. So you can see here I'm passing in the constant Cuda MemCopy host to device, and that says, not surprisingly, I'm going from the host to the device. The first two parameters are the pointers you want to copy between. And if you're going from host to device, well, just like MemCopy that you may remember from the C programming language, the first parameter is the destination. So like I started to say, if you said copy from host to device, this first parameter better be a pointer on the device. It's a pointer to memory that you probably allocated with Cuda malloc. Your second parameter better be a pointer to host memory, so maybe memory that's on the stack or global memory or memory that you malloced on the host. And then the next parameter is just how many bytes you want to copy. So looking at these two functions together, this is typically how you would get data onto the device. You load it into an array on the host, you'd malloc some space, or you'd Cuda malloc some space on the device, and then you'd call this to copy stuff over to that device. Then once you've done this, it's time to start up a kernel. You'll make a call to the function that you've defined as a kernel. Inside those triple angle brackets, you'll tell it the geometry of the threads you want to run. And then the main, or whoever called that kernel, will just wait for that kernel to execute. Like I've shown, Cuda will take care of firing up all the threads you ask for. It'll run as many as it can at once, and if it can't run them all at once, it'll schedule all of your blocks to run one after another, and then they'll be able to access them, whatever you copied, into device memory. Once that kernel has finished, if you had other things to do with that memory, you might just leave it on the device and then run other kernels. In our example program, we're just going to run one kernel, so once it's done its job, we want to copy something back to host memory so that we could take a look at it or save it to a file. Fortunately, the same function we just saw, Cuda MemCopy, does that. We pass in a different value of this last parameter. You can see from its name it says to go the other way. The size parameter is the same, so how many bytes do you want to copy? But the source and destination are reversed. So if you're copying from device to host, this first parameter better be a pointer to some block of host memory, and the second parameter better be a pointer to some device memory. So this is, for code running on the CPU, this is how it finds out results from what you computed on the GPU. Once you're done with a Cuda program, just like a C program, you have to start thinking about cleaning up after yourself. If there's a Cuda malloc for getting device memory, there's a Cuda free for freeing it. So you call Cuda free, you give it the address of a block of device memory that you previously allocated, and that frees it on the device so that you could use that same memory for something else later. Normally, well, my pictures don't show this, but normally if you had some host memory, you might call free to free that up. And then right before you finish, there's a call to Cuda device reset that tries to put it back into a sane state. If you made some mistake along the way, this should put the device back into whatever state it was when you started running it. If you look at my program example, you'll see I call this at the very end, right before I exit. So I've got an example. We'll take a look at this. We'll try it out interactively. It'll be a demonstration of a lot of the calls that we've seen. What does it do? Well, it does a lot of what we talked about, except it just uses nonsense data. So at the start, it makes a big array. I think it's about 50,000 random integers between 0 and 999. It allocates space on the device and copies the contents of that array over. And then it creates or runs a kernel with a thread for each item, or for each data item in that array. Which means, well, if I'm making 50,000 items in my array, I'm going to turn around and ask Cuda to make 50,000 threads for me. That'd be a lot of threads on a general purpose CPU. That's normally not how you'd use a general purpose CPU, but that's fine for the GPU. So the GPU can handle that many threads, maybe not all at once, but it'll schedule them to run as many at a time as it can, or at least as many blocks as it can handle. And then once the kernel has finished, we'll copy the same array back into host memory, and then we print out what's in it. I think we don't print every element because I don't want to see 50,000 values, but I think we print every 100th element or something like that. In the initial version of this program, the threads don't do anything. So when we copy back that block of data, we get the same values we copied over. But we'll make some, after we run it and give it a try, we'll make some changes to it, like we'll add code to zero out every element. We'll take that out and we'll add code to just increment every element. And then, like like my bullet down there suggests, we'll try to add up all the elements, but you'll see if you're not careful with that, or if you don't think about it, it's easy to make some mistakes. But those are mistakes that you're already good at thinking about. They're the same kinds of things you always have to worry about with potential race conditions. What happens if a thread accesses a value and another thread might be modifying that value? All right, let's give this a try. So we've talked about how the Cuda API works. I thought we'd give it a quick try just to show some of the things we've been seeing. To do that, I've got to log in here. It's logged into one of the university Linux machines. And like we said, when you were activating your account, to get to one of the Cuda machines, you'll need to get there from a system on campus. I've already gone through setting up a key pair and activating it with Arc, so I should be able to log right in. To do that, I'm first going to log in to the head node of the Arc cluster, so SSH, just like you did in the previous assignment, arc.csc.ncsu.edu. And here I'm logged into Arc. Arc is a collection of more than 100 different systems and 100 different nodes. When you log in, you get a shell connection to the head node. And you can see you have access to all of your files, but not the ones you're accustomed to seeing. These are files on the Arc system. It maintains its own file system that's shared between all of its nodes, but it's not the same file system. It's not AFS that you're accustomed to. So if you want to work with files between Arc and other university systems, you're probably going to have to transfer them back and forth, at least initially. You have some file space here, and as long as your account is available, you can access these files here. So you might want to upload your code that you're going to work on it here on the Arc machine, and then maybe download it once you've completed it so you can submit it. So I'm here logged into the head node. This is where you go when you first connect to the machine, but it's not a good node to work on. I'm not even sure it has a graphics coprocessor on it. So the first thing I'm going to do is connect to a compute node. To do that, we need the srun command -p GTX 480. So for that part, I'm just asking for a particular type of compute node, one that has this kind of graphics adapter. The srun command is for scheduling jobs on Arc. You might have a job that's going to run across multiple nodes, and you may need to schedule it to run later, and this command would do that for you. But in our case, we want an interactive job. We want to get a shell prompt on one of these nodes. So to do that, we need pty/bin/bash, and then I'll go ahead and hit enter on that. If the system was very busy, I might have to wait a little while here to get access to a compute node. I had to wait for a moment there, but it looks like I got connected to a compute node. You can see my prompt changed a little bit, and that shows me I'm on a system that that I can run Cuda jobs on. Be careful when you log into Arc. Be sure you don't start trying to compile big jobs or run jobs on the head node. That's for getting into the Arc system and then connect to one of these compute nodes once you've done that. So I thought we'd look at a quick example. I've got it here under the example directory. Oops. Oh, I said VI example instead of what I meant to, which is CD example. And it's called random list. This same file should be available from the course website. Let's take a quick look at it. Down here in main, so here's the top of main. Your program starts out running in main. And then, like we said, you can farm off jobs to the graphics coprocessor as needed. So first I'm going to generate a list of 50,000 numbers. They're just going to be random numbers. I just want to show off what you can do with Arc, so I'm not doing a particularly useful compute task here. I allocate space for 50,000 random numbers, and then I go in and fill them in using the rand function modded by 10,000. So I should get random numbers in the range between 0 and 9,999. Once I've done that, that gives me a list of random numbers on the host, but I need to get that out to the device so that threads running on the GPU can access that memory, can access that list. So the next two calls are what we just talked about before. I'm going to call CudaMalloc to ask for exactly that same amount of space. So number of items times how big each item is, but I'm going to get that space on the device. So just like malloc, once I've done that, I've got a region of memory. I get a pointer to that region. It's returned via this passbar address parameter. So now I'm on the host. I know about the location of this memory that I allocated on the device. I can't use it from the host because that pointer is the location of memory in sort of a different, on a different piece of hardware. But if I go to Cuda MemCopy, I can ask it to move memory back and forth, and here I'm asking it to take the random list I just generated, here's how big it is, and copy it onto that, into the memory pointed to by that pointer I just got. Once I've done this, I'm ready to start making some threads on the device and having them access parts of that list. So I'm going to get ready to run a kernel. To do that, I need to figure out how many I need to decide how big my blocks of threads are going to be and how many blocks I need in a grid of threads. I decided that I would put 100 threads per block, and then so the only thing I'll have left to figure out is how many blocks I need for the number of threads I want to make. I should have said earlier, my plan is I'm going to make a thread for every one of these 50,000 values I just generated. That's going to be a lot of threads, but it's not too many for a graphics processor like this to handle, so Cuda can take care of that. I just need to figure out how many blocks I need. So I take the number of items I made, divide it by the number of threads per block, and this little part here is for rounding up. It doesn't matter for this example because my number of items is evenly divisible by my number of threads per block, but if it wasn't, you might have a last block that has, you might need a last block where not all of the threads are used. Maybe some of them have a value to work on and others don't. So rounding up like this will give you enough blocks to have all the threads you need so that every thread can have a value, with the understanding that that last block might have some unused threads. We'll see that again when we start looking at our code for the kernel function. My function that's gonna run on the device is called do something. This is that invoking of a kernel that we talked about before. So this is from the host. I'm calling a function on the device. Over here is the name of the function. I just called it do something. These are the parameters out here. So I'm going to give it a pointer to the list I just made and the number of items in the list. And the stuff in between inside these triple angle brackets, that's sort of the geometry of my computation. So here's how many threads I want in each block, 100. And here's how many blocks I need, so whatever I figured out above. And then if this succeeds, we'll go ahead and look at the rest of the code. If this succeeds, if I want to get the results back from these threads, I need to get something out of their memory into the host memory. I'm going to have my threads just leave their results in that same list that I gave them. So when I'm done, I copy from the contents of that list back to the list I allocated in host memory, and then I go through and print out the values. Not every one of them, because that'd be 50,000 values, so I just print out every 500th value or so, and that'll let us sample what's going on in the thread without having sample what's going on the device without having quite so much output. When I'm done, I clean up, I free the memory I allocated on the device, I free the memory I allocated on the host, and then last is this call to Cuda device reset that we talked about before. That should put the device back in the same state it was when my program started executing. So that's most of the code that could run on the host. There's an error handling function up here, which is just if something goes wrong. And then here's the interesting part. This is the code that's going to run, that every one of my threads is going to run. So when I call that do something function down in main, it runs this function up here, but not just on one thread. It makes the 50,000 threads that I asked for in blocks of 100 threads each. And when each thread wakes up, it gets copies of the parameters. So it knows where my list starts, at least it knows that device pointer that I handed it, so it knows where the list lives in device memory. And every thread knows how big the list is. You'll remember in P threads we had to worry about passing parameters like this to our threads, and that might take a little bit of thinking and a little bit of code, but here Cuda does a lot of this for us. Another thing it does for us is, I said when your threads wake up, they know something about who they are. They know their index within their block, and they know their block's index within the whole grid. And you can use this to essentially assign different jobs to each of your threads. It's an easy way of generating a unique index for each thread. So that's what I'm doing here. This variable block index is one you get for free in Cuda. You don't have to figure out the value of that. It's done for you when your thread wakes up. But it tells you within all the blocks which one are you. And block index X is just, we mentioned how blocks and grids can be multidimensional if you want to assign jobs to your threads that might relate to images where you've got 2 dimensions to worry about. Here we're only using the first of those multi-dimensions, so we're sort of thinking of our threads as being in one big line. So, among all the blocks, which block are you? Among all the threads, which thread are you? So if I take your index of your thread plus the index of your block times how big each block is, that should assign a unique index to every thread, counting from 0. Like I said before, if we had a number of items that wasn't perfectly divisible by our block size, we might have to worry about some threads in that last block that don't really have a value to work on. We don't for this example, we don't have to worry about that, but I added the code for it anyway. If you compute your index and it's past the end of the list of items, so the list of items is 0 up to but not including count. So if you've got an index that's within that range, you've got an item to work on. If not, you've got nothing to do. So inside this if is where I could put some code to actually do something. You can see I don't have any code for that yet. We'll add that in a moment, but first I thought we'd give this, let's go ahead and try compiling and running this program as it is, and then we'll start adding code to make it do things a little bit differently. So let's quit out of our editor and go back to the shell prompt. We're going to compile this program, but before we do, we have to enable the Cuda compiler. So to do that, we'll run module load Cuda. You should only have to do this once each time you log in. It tells, tells the system about the Cuda compiler. There may be some other things that this enables when you run it, but once you've run it, that stuff is enabled for the rest of this shell session. So unless you log out and log back in, you shouldn't need to do this again. And then once you've enabled or once you've loaded up Cuda, it made it available to run, the compiler you'll use is called NVCC. You can see from its name, it's kind of like the C compiler. And this NV in front is for NVIDIA, the developers of Cuda. This compiler doesn't take as many options as what you're probably used to with GCC. Things like enabling all warnings and using the C99 standard. But even without those options, it's going to be able to compile this simple Cuda program that we wrote. The good thing is the rest of the options are probably what you're accustomed to. You'll give the name of your source file, random list. And then if I didn't give anything else, it would just write out an executable called a.out. I'm going to tell it to write my executable to random list. And then when you run this compiler, I think every time you're going to get this warning. I would say don't worry about that warning too much. It looks like it's warning us that some targets that our compiler used to be able to write code for are no longer going to be available. Whether or not we are using those targets, this compiler seems like it still works, or has still worked for me. So until this changes, I think we'll be okay with that. You can see now, in addition to my source file, I've got an executable. To run this, you just run it like a regular program. When this program starts up, it takes care of farming off work to the GPU every time you try to run a kernel. When it starts up, it takes care of getting that GPU code into getting that GPU code into the memory for the GPU. All right, so enough stalling. Let's give it a try. All right, our program started up, it generated this giant list, it pushed it over to the device's memory, it woke up 50,000 threads that all computed their index and then pretty much did nothing. They exited, and then in main, we copied that list back and printed out every 100th item. And you can see, well, plausibly, that looks like a list of a bunch of random values. I'm going to look at this last one in particular, because in a moment, we'll make a change. This last one ended up being 6520. And every time we run this program, we should get the same pseudo-random sequence of values, because that's how rand behaves in C. It doesn't reseed the random number generator for you. So in this version of the program, our threads aren't really doing anything. Let's make them do something. So here, once I've figured out that I have an item to work on, let's change it. Let's just set it to 0. So every thread will be responsible for clearing its its index in this big list. I may not have done a good job explaining that before, but my plan here is I'm going to make 50,000 threads. They're each going to use their index to decide an item in the list that they're responsible for. And then down here, they're just going to each clear their items. So list at I equals 0. We'll see in a moment, they can all access every element of the list. It's in what's called device global memory, so all of your threads can access it. Maybe not all at the same time, because remember our threads are being organized into blocks, and each block is being run possibly one after another, maybe multiple blocks at the same time, if they're not too big. So every thread could access every element of this list. I'm just writing my code so that every thread chooses to work on the ith element of the list. So every thread sort of has its own part of the data to work on, and right now they're just going to clear it. So I wrote that out. Let's compile this and give it a try. I forgot to... Alright, yeah, I forgot to compile it. Alright, so I was going back through my command history. There's the line to compile it. And let's give it a try again. That looks better. So now they all managed to clear their item on the list. I didn't really need the power of a GPU to do that. But we can make it do more interesting things. Let's go into the same line of code, and how about if instead of clearing it, they each add, plus equals 1. They each add 1 to their item on the list. Recompiled, let's rerun. And you can see this is why I paid attention to that last value, because I knew I was going to do this add 1 example. Before it was 6520, and now it's 6521. So I'm going to say plausibly every thread has added 1 to its list item. I want to do one more thing to have the threads do something a little bit more interesting, but also to show how you have, like I said before, how you have to be careful whenever you're writing multi-threaded code, and you have to think about race conditions. So let's do something that's going to end up exhibiting a race condition, even on a graphics device like this. Random. Alright, so I'm going to pretend that I don't know about this potential race condition. So my plan is here, instead of just adding 1 to my value or zeroing it out, how about if I go through all the values in the list? I mentioned the list is in global memory for the device, so I ought to be able to do that. How about if I go through all the items in the list and I just add them up? Let's have a variable sum. We'll start it out at 0. Let's go through the whole list. I have to use j because I've already, well, I'm going to use j because I already used I for my own index. J equals 0, j is less than count, j plus plus. So I'm going through the whole list, and then for each item, sum plus equals list at j. And then once I've computed that, we'll take the sum and we'll write it back into our element of the list. So when this is done, every element of the list should have the sum of every element that started out in the list. This is, well, every thread is going to be sort of adding up its own copy of the sum at the end. Since they're all adding up the same stuff, it should all agree at the end. This shows how they can all work together, but it's not what you'd typically do. Normally, if you're going to have your threads all do some work, you'd have them all work on slightly different things. There's no point duplicating that computation. But still, this shows a little bit more about what threads can do. So when we're done, I'll just take sum and I'll copy it to my element of the list. Alright, so I think I'm ready to go. Then down at the bottom, when I print out those values, I'm still printing every 100th value, but they should all be a sum of the list of randomly generated values. Let's compile it. Alright, so we didn't make any syntax errors. But when we run this program, you can see we made a logic error. You might look at this and initially think, well, that's overflow. But the values we're working with shouldn't be big enough to overflow. We've got 50,000 items, each one no bigger than 10,000. So even if we added all those together, it shouldn't be any bigger than 500 million. Yet we've got negative numbers in here, we could check, but I bet we've got some values bigger than that. What went on here? Well, it's the same thing we'd have to worry about whenever we're writing multi-threaded code. All these threads are running potentially many of them in parallel. They're all planning on looking at a list and adding up its values, and that's fine. But they're also all planning on changing their part of the list when they're done. And that may not all happen at the same time. If one thread gets to run, or if its block of threads gets to run earlier, it may modify its element of the list before someone else even gets to look at its element of the list. So in some cases, we've got values that are being added up that are already the sum of a bunch of values, and in some cases we're not. So we're getting, we are in fact getting some overflow because we're not really doing the thing we planned on with this computation. So that shows, I guess, a way to solve this would be to, an easy way to solve it would be to not modify the list that you're using while you're using it. You could easily have a second array on the device, and you could write results to that without modifying your input value, and then that would work just fine. That's kind of what I'm expecting you to do on the next homework assignment. I'll show you quickly one more example that shows how you can do stuff on the device. You can put some real computation there, but this example, unlike what I just showed, this example works. Instead of writing it here, I'll just go take a copy of it. I got a copy. It's saved up here in my clean example folder, and it's called, oh, it's called primes.cu. Copy it to here. Let's take a quick look at that. Fortunately, this is really just another variant of the random list we were just looking at. Most of the stuff is the same. If you look down here in main, it generates a random list, shoves it over to the device, makes a bunch of threads, one for every element on the list. When it's done, it copies the list back over to the device. But then, instead of just printing out every value, I just add them all up. My plan, and you can kind of see from the name, my plan is I'm going to count how many of those items are prime. Every thread gets a value. It does a primality test on it. And then once it's done that, it writes back into its element of the list, 0 if it wasn't prime, and 1 if it was prime. So kind of like a true-false value, but one that I can just add up if I want. So I go through the list, add up all the items, and wherever there was a prime there, that should be a 1. So I should get the number of primes on the list. Now I've got some bigger computation that's going on in each thread. If you take a look up here, well, do something didn't get a whole lot bigger. Every thread figures out its index. If it has a value to work on, it just calls this isPrime function, passing it its value. And then the job of that isPrime is to return 0 or 1. It just saves that in its list. So here we are modifying the list, just like we were before, but every thread is just looking at its own element within the list. So even if some threads have modified their values in the list before I get a chance to look at mine, I wasn't looking at their values anyway, so that shouldn't affect me. Up here in the isPrime function, well, it's a typical primality test. For tiny little numbers, they can't be prime. For other numbers, I'll go look for a factor, and I won't look past the square root of the number. If I find a factor that evenly divides it, it's not prime. If I make it through all the potential factors and I don't find one, it must be prime. I guess the interesting part about this is this part at the front. We said before, if you have a function that's compiled for the device and it needs to be called by other code on the device, just like down here, I'm running in a thread, I call isPrime, it's defined, it's compiled to code that runs on the device, so I marked it as a device function. Let's give this guy a try. It's got a different name, so I'm going to have to write a new nvcc command. I want to compile the primes function, and I want to write its output to primes without the cu. So if this works, you can see now we've got our threads doing something interesting, and they quickly figure out that in this list of 50,000 items, I ended up with about 6,000 primes. That's all I had planned to show for stuff running on the GPU. I'll go ahead and show you what you need to do once you're done with this. If you're working on a homework assignment, you'll want to make a copy of your program before you're completely done. To do that, you'd go back to another system on campus. Here I need to get out of first the compute node that I'm using. So I'll exit. This drops me back to the head node of the ARC cluster. I can type exit again, and that drops me back to being logged into an ECS machine. And like I started to say a moment ago, from here you could SFTP over to ARC and get a copy of the program that you just wrote. That's all I plan to show you for examples on GPU programming. Remember, we've got that one example random list for you to use, and for your homework you get to do something a little bit more interesting than what we did here. Thanks for your attention. I'll see you next